Hello my dear students, in this video now we are going to discuss about the conductometric titrations. In conductometric titrations, conductivity or conductance of the solutions is measured by using the conductometer. There are many types of conductometric titrations, but here we are going to discuss about the three types of conductometric titrations. First one is the acid-base titrations, and the second one is the precipitation titrations, and the third one is the complexometric titrations. Now first of all we discuss about the acid-base titrations. Here acids are two types, strong acid and weak acid. Similarly, bases are of two types, strong base and weak base. So on the whole we have the four types of titrations, acid base titrations. So here among them first one is the strong acid versus strong base titrations. So in these titrations we take NaOH base or alkaline solution in the burette, and we take the acid solution in the beaker like this, and in this beaker we keep two electrodes and which are connected to a conductometer, and here slowly we go on adding the NaOH solution and we measure the conductivity. So when we add the NaOH to the HCl solution, this type of reaction takes place, HCl and NaOH, and gives us to the NaCl and water. So here we know very well that here acid is strong as well as base is also a strong one. So when we add to the water, they completely dissociate. HCl completely dissociates into H plus and Cl minus ion, and NaOH completely dissociates into the Na plus and OH minus ions. So here we would remember that the molar conductivity of the H plus and OH minus ions is almost same. So in the beginning, the number of the H plus ions is very high, and as a result, the conductance or conductivity of the solution is also very high. As we go on adding the NaOH solution, the OH minus ions of the base NaOH react with the H plus ions of the acid. As a result, the number of the H plus and OH minus ions decrease. So as a result, the conductance or conductivity gradually decreases. And after the complete neutralization, in this one there are no H plus ions to react with the OH minus ions. So the OH minus ions number goes on increasing. So as a result, what happens, the conductivity also increases. So here if we extrapolate these two type of lines, here we get the end point, which is known as the equivalence point. So here this type of graph we get in the strong acid versus strong base titrations. Now we discuss about the strong acid versus weak base titrations. Here base is weak, so it does not dissociate completely, and always a equilibrium is established between the dissociated ions and undissociated molecules, and HCl is a strong one. As a result, it completely dissociates and gives the H plus and Cl minus ions. So in the beginning, the number of H plus ions is very high. As a result, the conductance or conductivity is also very high, and as we go on adding the ammonium hydroxide, what happens, the H plus ions of the HCl react with the base ammonium hydroxide and form ammonium chloride and water. Due to this, the number of the H plus ions gradually decrease. As a result, the conductance gradually decrease, and after complete neutralization, there are no H plus ions to react with the ammonium hydroxide, and we know very well that ammonium hydroxide is a weak base, no? So we don't get more number of the OH minus ions because it is a weak base and does not dissociate completely. As a result, there will be no much increase in the number of the OH minus ions, so that there is no increase in the conductance of the solution. So that's why we get a straight line like this. Now we go for the weak acid versus strong base titrations. Here acetic acid is the best example for weak acid, and NaOH is example for the strong base. As the acid is very weak, this type of equilibrium exists between the ions formed due to the dissociation and the undissociated molecules. So in the beginning, the number of the H plus ions is very less because acid is very weak. So and as we go on adding the NaOH, what happens? This type of reaction takes place and the salt forms. So this due to the increase in the number of this type of ions, we observe a gradual increase in the conductance of the solution. And after the reaction is completed, that means neutralization is completed, the number of the OH minus ions goes on increasing because there is no acid here. So as a result, we observe a abrupt or a sudden increase in the conductance of the solution. So as a result, we get this type of graph in this type of titrations. The fourth type of the acid base titration, that is the weak acid versus weak base titrations. Here both the acid and bases are weak. So in the beginning, as the acid is very weak, we observe less conductivity, and as we go on adding the ammonium hydroxide, that means weak base, neutralization reaction takes place and ammonium acetate salt is formed, and the salts are highly ionizable, so that's why they increase the number of ions. As a result, we observe the increase in the conductivity of the solution. And after that, that means after the neutralization reaction is completed, there is no choice for the formation of this type of salt or ions. As a result, the conductance of the solutions remains constant because the ammonium hydroxide is a weak base and there is no further number of ions furnished by this ammonium hydroxide. Now we take the summary of the acid base titrations. Look here, strong acid versus strong base titrations, strong acid versus weak base titration. Here in both these cases, acid is strong. As a result, what happens? And we are adding the base from the burette. So in this type of titrations, what happens? The number of H plus ions decreases. As a result, we observe a decrease in the conductance. Okay, na? And here weak acid versus strong base titration, and this is the weak acid versus weak base titrations. So here weak acid, and in this case, due to the addition of the base, what happens? The salts are formed. As a result, we observe increase in the conductance of the solution. And here strong base, and here also strong base is there. So when the strong base is added, we observe abrupt or sudden increase in the conductance of the solution. Here also. And when the base is weak, there will be no change in the conductance of the solution. So here we observe a constant value, and here also we observe a constant value. Strong acid, we observe first decrease. Weak acid, we observe increase. Okay, na? And strong base, so we observe increase after neutralization. And weak base, and the conductance remains constant after neutralization. So like that we can easily remember. Now we discuss about the precipitation titrations by taking the reaction between the KCl and silver nitrate. Here we take the silver nitrate in the burette, and KCl solution is taken in the beaker or conical flask. Okay, na? So, and we have to remember that the molar conductivity of the chloride and nitrate ions is almost same, and the molar conductivity of the potassium ions is greater than the molar conductivity of the silver ions. So in the beginning, potassium chloride is there, and due to addition of the silver nitrate, what happens? This type of reaction takes place and we get the silver chloride and potassium nitrate. So before and after the reaction, potassium ions are present, and here chloride ions are removed due to this reaction, but nitrate ions are added. So there will be no much change in the conductance or conductivity of the solution. As a result, unto the neutralization point, the conductance remains constant. But after the reaction is completed, silver ions remain in the solution, very free. So as a result, what happens, the conductance of the solution gradually increases. So in this type of precipitation, we get this type of graph. Now we go for the complexometric titrations by taking the reaction between the potassium chloride and potassium chloride and mercuric perchlorate. Here we have to remember that molar conductivity of the chloride ions is slightly greater than the molar conductivity of the perchlorate ion. Here in this step titrations, we observe two types of endpoints here like this. Here, why? Because the formation of this complex compound, that is potassium tetrachloro mercurate or hydrogenate, occurs in two steps. So in the first step, what happens, mercuric perchlorate reacts with the potassium chloride and forms insoluble mercuric chloride and potassium perchlorate. Perchlorates are highly soluble, but here as the number of the chloride ions is goes on decreasing, what happens, we observe decrease in the molar conductivity of the solution. And look here, in the second step, what happens, the potassium chloride added through the burette reacts with the mercury chloride precipitate and forms the complex compound. But due to this, we don't observe any increase in the molar conductivity, because what happens, number of the chloride ions decreases, but the number of the potassium ions increases. So decrease in the number of the chloride ions and increase in the number of the potassium ions makes the conductance constant. But after the complex formation is completed, then chloride ions and potassium ions number goes on increasing. As a result, what happens, we observe increase in the conductance of the solution.